We are in chapter 4 where we're discussing bending. This is the 34th session overall. Here we continue discussing unsymmetric bending and look at examples. This is a roadmap of the sessions covered in the first 4 chapters. We are in session 34 where we will discuss unsymmetric bending analysis and examples. We find out the product of inertia in the xy plane. We could have found the product of inertia in the yz plane as well. However, the results we get of the product of inertia in the xy plane can easily be transferred to the yz plane. We have an unsymmetrical section here shown by the shaded portion. O is the centroid of the section. To start with, we arbitrarily take two orthogonal axes, x-axis and y-axis. Then the moment of inertia Ix and Iy are given by these expressions, and the product of inertia is given by this expression. We then rotate the coordinate system by an angle theta. So this is the x dash axis and this is the y dash axis. We'll now find Ix dash, Iy dash and Ix dash y dash. Consider an element at the point C. It is at a distance x and y when we consider the initial xy axis. It is at a distance x dash and y dash when we consider the x dash y dash axis. We'll first find out x dash and y dash in terms of x, y and theta. We use the triangles ODA and CAE. OA is x, so OD is x cos theta and DA is x sin theta. They are given here. Now CA is y, so CE is y cos theta and AE is y sin theta as given here. We also have BE equal to EA and BB equal to AE. Now x dash is equal to OD plus BB. OD is x cos theta and DB is y sin theta. So we get x dash is equal to x cos theta plus y sin theta. CE is equal to CE minus BE. We earlier obtained CE and BE. So y dash is equal to y cos theta minus x sin theta. Ix dash is equal to integration y dash squared dA. We earlier obtained y dash in terms of x, y and functions of theta. Substituting, squaring and then integrating, we get Ix dash in this form. Here 2 cos theta sin theta can be written as sin 2 theta. and cos squared theta and sin squared theta can be written in terms of cos 2 theta. So I x dash is given by this expression. Rearranging, we get I x dash is equal to ix plus iy divided by 2 plus ix minus iy divided by 2 cos 2 theta minus ixy sin 2 theta. Similarly, iy dash is equal to integration x dash squared dA. Substituting, squaring, and then integrating, we get iy dash. The terms in these two equations are the same. However, there is a change in sign. Ix dash y dash is equal to integration x dash y dash dA. We substitute x dash and y dash using these two expressions. We then multiply and integrate. We have three different integrals. These two integrals can be written in terms of sine 2 theta. This integral can be written in terms of cos 2 theta. So rearranging, we get ix dash y dash is equal to ix minus iy divided by 2 sine 2 theta plus ixy cos 2 theta. We can find the angle at which ix dash y dash is equal to 0. So substituting 0 in the left hand side, we find that tan 2 theta is equal to minus 2 ixy divided by ix minus iy. The theta obtained by this expression is the angle at which the product of inertia will be 0. Since tan 2 theta is equal to tan 180 plus 2 theta, we get two values of theta. These two values give the direction of two principal centroidal axes. So we can start with two arbitrary axes and find out the direction of the axis at which the product of inertia is 0. We now know the way to find out the principal centroidal axis, that is the axis with I, yz is equal to 0 in an unsymmetrical section. Here we give an overview of all the cases we have to deal with. The overview is given in two groups. So here we will be dealing with the first group of cases. With this group of cases, we considered that the load and the moment will be applied on the principal centroidal axis. We earlier discussed at the beginning of this chapter that there can be three types of sections. So this is a rectangular section which has two axes of symmetry. This channel section has one axis of symmetry, and this angle has no axis of symmetry. In this case, if the moment is applied about one or both axes, then we can use the flexure formula to find out the stresses. The flexure formula is used with each axis individually, and then the stresses are added up algebraically. With this section, which has one axis of symmetry. We just found out for a section which has I, Y, Z as 0 on one axis, the other axis with I, Y, Z is equal to 0 will be perpendicular to the first axis and pass through the centroid. So in this case as well, if the load is applied or moment is applied on one axis or both the axes, we can find out the stresses using the flexure formula. In this case, we know the centroid only to start with. Now we can choose any y and z axis and find out the moment of inertia and the product of inertia for that set of axes. We can then find out the rotation that is needed to move to the axis which has I, Y, Z is equal to 0. That is the principal centroidal axis. Here we have shown the principal centroidal axis. Now consider the load or moment applied along any of these principal centroidal axes or both of these principal centroidal axes. Then using the flexure formula as before, we can find out the stresses along the section at any point of the section. Here we discuss the second group of cases. The moment in this group of cases is not applied along the principal centroidal axis as in the last group. We deal with three types of sections as earlier mentioned. This section has two axes of symmetry. This section has one axis of symmetry, and this section has no axis of symmetry. The direction of the moment vector has been discussed earlier. It is shown using two arrows, and this is the right hand with the fingers clasping along the direction of the moment and the thumb showing the direction of the moment vector. In this figure, the moment and the moment vector is not along any axis. So this is the moment and this is the moment vector. Moment being a vector can be resolved into a horizontal and a vertical direction as has been shown here. So if this moment is m, then the moment along the horizontal axis is m cos theta, and the moment along the vertical axis is m sin theta. We have earlier discussed the case where two different moments have been applied about the y-axis and the z-axis, and using the flexure formula, we have been able to find out the stresses at any point in this section. So for this case, we can use the same procedure. Here we have a rectangular case where the rectangle is at an angle to the initial y and the z axis. And in this case, it is shown that the moment is applied about the z-axis. So the moment vector is along the z-axis. In such a case, we have to choose a new set of y and z axes along the axis of symmetry as shown here. And then the moment is resolved along the two axes of symmetry. Here we can use the flexure formula again about the principal axis to find out stresses at any point on the section. Now consider a channel as shown. It has an axis of symmetry, which is the axis with I, Y, Z is equal to 0. As earlier discussed, we can find the other axis with I, Y, Z is equal to 0 by taking an axis perpendicular to the axis of symmetry and letting it pass through the centroid. If the moment applied has the moment vector that does not coincide with any of the principal axes, then we can resolve the moment vector into two vectors that act along the two principal axes. We can then use the flexure formula and find out the stresses at any point in the channel section. Here, a case of the angle of the channel is shown, which is similar to this case. Here, the moment is applied so that the moment vector coincides with one of these y and z axes. But the y and z axes are different from the principal centroidal axis of the channel section. Here, the moment vector can be resolved along the two different principal axes. We then can use the flexure formula and add the stresses algebraically to get the stresses in the section. This section has no axis of symmetry, but we find out the principal centroidal axis. If the moment vector does not align with any of the principal axes, then we resolve the moment vector so that we get two vectors along the principal axis. We can then use the flexure formula and find out the stress acting on the section by adding the stresses algebraically. Here we find the direction of the neutral axis for a rectangular section where the moment applied is not aligned with any of the centroidal principal axis. The moment applied is at an angle theta with the horizontal z-axis. We resolve the moment vector into m cos theta along the z-axis and m sin theta along the y-axis. Then the stress of the moment about the z-axis on this section is given by this expression, and the stress of moment about the y-axis on this section is given by this expression. For this arrangement of coordinate axes, earlier we had given the algebraic equation for sigma x. Now that we have mz and my, we can substitute that in the algebraic equation. At the neutral axis, stress is 0, or we get this equation. We can write this equation as y divided by z is equal to tan theta iz divided by iy. Now, if the neutral axis makes an angle phi, then tan phi is equal to tan theta iz divided by iy. In this section shown, iz will be larger than iy. So, which means that phi will be larger than theta, which is shown in the diagram here. We notice that for this case, where only a moment is acting, though it is not about any principal centroidal axis, the neutral axis passes through the centroid. But as we had earlier seen, if there's a force acting on the centroid, then the neutral axis will not pass through the centroid. Here we have a case of a rectangular beam subjected to a moment which is not aligned with any of the axes of symmetry. We resolve the moment vector along the y-axis and the z-axis as shown. Note that in the previous examples, we had taken the direction of the moment vector to align with the positive direction of the z-axis and the y-axis. But here, the direction of the moment vector is not aligned with the positive direction of the z-axis. So, mz that we have found out using m cos theta is a negative moment. My is a positive moment. We find out the moment of inertia Iz and Iy. To determine stress, we use the same algebraic formula that we used for this direction of axis earlier. Here, however, mz is negative. So when we substitute, we get an expression that is positive in both y and z. In order to find out the stresses at A, B, C, and D, we substitute the dimensions of the point A, B, C, and D, and we get stresses at A and B that are positive and stresses in C and D that are negative. Here we have a semicircular section with the moment applied as shown in this diagram. The coordinate axis, that is the y-axis and the z-axis, are chosen. The centroidal distance from the base is given as 4r by 3 pi. So the coordinate axis passes through the centroid. The moment is resolved along the y-axis and the z-axis. We also find out Iy and Iz, which are given by these two formulas. One can note that the direction of the resolved moment vectors are the same as the y and the z direction. So the resolved moments are both positive. Now substituting all the values in this equation, we get stress in terms of y and z. Substituting the ordinates of A, B, and D in this equation for sigma, we get the stress at A, B, and B. Here we have an example of an I section to which a moment is applied as shown. The dimensions of the I section are given and we are required to find out the stresses at A, B, D, E. We are also required to find out the angle that the neutral axis makes with the horizontal. With the I section, the principal centroidal axis aligns with the axis of symmetry. The positive direction of the y and the z axis are chosen so that the resolution, the moment vector in the two directions aligned with the positive values. Also, y and z are chosen so that sigma can be given by this equation. We are given Iz and Iy. We find out Mz and My and we substitute in this equation so that we get an expression of stress in terms of y and z. The ordinates of A, B, D, and E are known. We substitute the ordinates in the equation for stress to get the stress at A, B, D, and E. The angle that the neutral axis makes with the horizontal is given by this equation. You can find out phi. In this problem, Iy is less than Iz, so phi is greater than theta. We are given this section with dimensions as shown. A y and z axis are given and the moment is applied about the z axis. We are required to find out the stress at the point A. The section is not symmetric and the y and z axes that are given are not the principal centroidal axis. Initially, from the dimensions given, we find Iy, Iz, and Iyz. We earlier discussed that given an arbitrary set of axes, we can find out the angle theta at which the product of inertia is zero. The formula was initially found using xy plane. We can change it to yz plane. So the angle at which the product of inertia zero is given by this expression. Find tan 2 theta and two values of theta that satisfies this equation. The negative value means clockwise rotation and the positive value counterclockwise rotation. Note that if there's a 90-degree rotation, then ix dash y dash is equal to minus ixy. So if there's a 90-degree rotation and the product of inertia is 0, then with the rotation, the product of inertia will still remain 0. So instead of using these two axes, we have used these two axes. So this angle has been considered as theta. Using Iy, Iz, Iyz, and the theta we have found out, we determine Iy dash. We also determine Iz dash. So the axes y and z given were the arbitrary axes, and we have now found out the axis at which the product of inertia is 0, and also found out y dash and z dash. Till now, we have found out the axis y dash and the axis z dash for which the product of inertia is 0. So we have found out the angle theta. We have also found out Iy dash and Iz dash. Here we are required to find the stress at the point A. The moment was initially applied about the z-axis. We have taken components of the moment about the z-dash axis and the y-dash axis. My dash is m cos theta. Mz dash is m sin theta. In both these cases, the direction of the moment vector coincides with the direction of the axis. Hence, both the moments found my dash and mz dash are positive. To find the stress at point A due to the moment mz dash, we need the ordinate y dash. And to find the stress at point A due to my dash, we need z dash. So now we'll find out y dash and z dash. A line is drawn here from the point A perpendicular to the z dash axis. It will help us to find y dash. Let us consider that this line cuts the y-axis at B. We have denoted different points in this diagram by different letters. Initially, we know the vertical and the horizontal distance of the point A. So we know AI and IE, or we know DP. This angle is theta. So knowing DP, we can find out AP and AT, which has been found out here. Since we know AI and now we know AT, we can find DI, which is also equal to BE. So we have found out DI or BE here. Knowing BE, we can find out BC. This angle is also theta. So we have found out BC. Y dash is AB plus BC. We have found out AP and BC, and both are added to get y dash. Let us now find z dash. We know this horizontal distance EI. This angle is theta, so we can find out Fi. So here we have found out Fi. AI is given, and knowing Fi, we can find out AF, which is shown here. This angle HAF is theta. So we can find out AH. So here we have determined AH. As per the ordinate system, Z dash is minus AH. When the Z axis is 90 degrees counterclockwise to the Y axis, we have given stress by this formula. Here also the Z dash axis is 90 degrees counterclockwise to the Y dash axis. So the stress here is given by this formula with Y dash and Z dash in place of Y and Z in this formula. For the point A, we have found out Y dash and Z dash, and so we can find out the stress at point A. The stress due to both the moments come out as negative. You can check the stress physically. The arrow head due to M Z dash points in the quadrant of which A is a point. Similarly, the arrow head of M Y dash points to the quadrant of A. So the point A will be under compressive stress due to both moments. We have an equal angle here which has been taken from the table. A moment M0 is applied as shown. The maximum allowable stress is given, and we are required to find out the maximum moment that can be applied. From the tables, Iy and Iz are known. Also, the radius of gyration about the z dash axis is known. Since we are given the area, we can find out Iz dash. We then use the transformation formula of Iz dash with theta as 45 degrees. Substituting appropriate values, we get Iyz. We'll use this value of Iyz to find Iy dash in the next slide. Here we have an equal angle that is subjected to a moment m0 about the z-axis as shown in this diagram. We are given the maximum allowable stress, and we are required to find out the maximum value of m0 that can be applied. We were given Iy and Iz, and earlier we found out Iyz. Since this is an equal angle, it has an axis of symmetry which is given here as the y dash axis. So this y dash axis and this z dash axis, which is perpendicular to it and runs through the centroid, are the principal centroidal axis. So we attain the y dash axis by a 45-degree rotation from the y axis. The fact that the product of inertia about the y-dash axis is zero can be seen from this equation. Here Iy and Iz are the same and cos 90 is zero. So I y dash z dash is zero. This is the formula for I y dash, and substituting appropriate values we get the value of I y dash. Also substituting appropriate values we get the value of I z dash. We now look at the moment. The moment is applied about the z-axis, which is at 45 degrees both to the y-dash axis and the z-dash axis. So the components are m0 divided by root 2, both about the y-dash axis and the z-dash axis. The points where the stress can be maximum are A dash and B dash. We first find the stress at A dash. For A, we are required to find these two dimensions, y dash and z dash. We know AC, and since this is a triangle with 45-degree angles, AB is equal to AC. Also, knowing AC, we can find BC. They are given here. Now we know AD and we just found out AB, so we can find BD. It's given here. BE is BD cos 45. So now we can give Z dash since it is equal to CP plus BE, which is given here. DE is also BD cos 45 and is equal to Y dash. We now look at the stresses at the point A and A dash. Due to the moment about the z-axis, the stress at point A is tensile. And due to the moment about the y-dash axis, the stress at point A is compressive. In contrast, due to the moment about the z-dash axis, the stress at A dash is tensile. And also due to the moment about the y-dash axis, the stress at A dash is tensile. So we find out the stress at A dash since it will have higher stress. At A dash, Z dash is positive and Y dash is negative. Since here we have the Z dash axis 90 degrees counterclockwise to the Y dash axis, we use this formula. Substituting appropriate values, we get sigma A dash in terms of M0. Here we have an equal angle that is subjected to a moment M0 about the z-axis as shown in this diagram. We are given the maximum allowable stress and we are required to find out the maximum value of M0 that can be applied. We were given Iy and Iz, and earlier we found out Iyz. Since this is an equal angle, it has an axis of symmetry which is given here as the y-dash axis. So this y-dash axis and this z-dash axis, which is perpendicular to it and runs through the centroid, are the principal centroidal axis. We attain the y-dash axis by a 45-degree rotation from the y-axis. The fact that the product of inertia about the y-dash axis is 0 can be seen from this equation. Here Iy and Iz are the same and cos 90 is 0. So y dash z dash is 0. This is the formula for I y dash, and substituting appropriate values we get the value of I y dash. Also substituting appropriate values we get the value of I z dash. We now look at the moment. The moment is applied about the z-axis, which is at 45 degrees both to the y-dash axis and the z-dash axis. So the components are m0 divided by root 2, both about the y-dash axis and the z-dash axis. The points where the stress can be maximum are A dash or B dash. We first find the stress at A dash. For A, we are required to find these two dimensions, y dash and z dash. We know AC, and since this is a triangle with 45-degree angles, AP is equal to AC. Also, knowing AC, we can find BC. They are given here. Now we know AD and we just found out AP, so we can find BD. It's given here. BE is BD cos 45. So now we can give Z dash since it is equal to CP plus BE, which is given here. DE is also BD cos 45 and is equal to Y dash. We now look at the stresses at the point A and A dash. Due to the moment about the z-axis, the stress at point A is tensile. And due to the moment about the y-dash axis, the stress at point A is compressive. In contrast, due to the moment about the z-dash axis, the stress at A dash is tensile. And also due to the moment about the y-dash axis, the stress at A dash is tensile. So we find out the stress at A dash since it will have higher stress. At A dash, Z dash is positive and Y dash is negative. Since here we have the Z dash axis 90 degrees counterclockwise to the Y dash axis, we use this formula. Substituting appropriate values, we get sigma A dash in terms of M0. Here we have an unequal angle and we are required to find out the stress at the point A due to the moment as shown. We are given Iy, Iz, the area of this unequal angle, tan theta, and R y dash. Y dash is a principal centroidal axis. As the other principal centroidal axis, Z dash be 90 degrees to y dash and pass through the centroid. Here, since ry dash is given, we can find I y dash. Also, since tan theta is given, we can find theta in radians or in degrees. Since we now know I y dash, we can use the formula for I y dash to find out I yz. With I yz obtained, we can find out I z dash. We can do a check by finding out theta again, which comes out as the same value. Given the moment acting about the z-axis, the components are found about the z-dash axis and the y-dash axis. This angle is theta, and we can find my dash as m sine theta and mz dash as m cos theta. In order to find out the stress at the point A, we need to find y dash and z dash, that is CG and FG. We are given these two dimensions, so we can find out dF. We are also given CT. Now this angle is theta, so the angle DCE is 90 minus theta. Knowing CD and knowing this angle, we can find DE. So here we have given DF, CD, and DE. Knowing D and using the sign of this angle, we can find CE. And knowing DF and DE, we can find EF. So CE and EF are given here. The angle EFG is also 90 minus theta. Knowing EF, we can find out EG. So now we know CE and EG, so we can give y dash. Also, knowing EF and knowing this angle, we can find out FG. FG is Z dash. The Z dash axis is 90 degrees counterclockwise to the y dash axis, so we can use this formula. We have obtained my dash, mz dash, which are both positive. Y dash here is negative, while z dash is positive. So we find out the stress at the point A. The stress due to both moments are positive. This can be checked physically if we consider the moment about the z dash axis. Then A will be under tensile stress, and if we consider the moment about the y dash axis, then A will also be under tensile stress.